playing with complex conjugates, basically. Some properties that can help solve problems. Now, the first one, hopefully is obvious. The modulus of z will always be the same as the modulus of the conjugate, because all we're saying is, how far is it from the origin? Well, if one's just a reflection of the other in the real axis, they've got to be the same distance from the origin. And speaking of reflection in the real axis, that means their arguments will be opposite in sign. One will have a positive argument, one will have a negative argument. There it is. Z conjugate, which I've been saying, well, remember that's x squared plus y squared, but now we can just simply think of it as the modulus squared. The modulus squared. It's much easier to say. And I think we mentioned this before, didn't we? So if you're finding the conjugate, you could add the two numbers together first, then do the conjugate, or you could find the conjugates and then add them together. You could end up with the same answer. Same with multiplication, same with division. And now the reciprocal of a complex number is much neater to write, because I now don't have to write over x squared plus y squared. I can simply say, it's the conjugate over the modulus squared. So reciprocal of a complex number, conjugate over modulus squared. Going to do this question. I think there was a very similar question in one of the Patel exercises. It's quite long how you end up doing it in that one. Using conjugates, this sort of question is actually quite quick. So we're told x plus iy is the square root of this wonderful complex number. We need to show the real part squared plus the imaginary part squared. By the way, that would be
modulus squared.
There he is. It is equal to 2. Okay, so there's our number. But if I square both sides, that's a bit easier to play with then. But now I'm going to play with conjugates. And because the order doesn't matter, what I'm saying is the conjugate of the left-hand side must equal the conjugate of the right-hand side. I mean, if the two things are equal, so their conjugates have got to be equal as well. But with the division, I can do the conjugate of the top divided by the conjugate of the bottom. But then, the x plus iy squared, yes, I could do x plus iy squared first, then find its conjugate, or I could find the conjugate, then square it. So that's what I've done. I've decided to take the conjugate and then square it on the left-hand side. So x minus iy squared. So if I multiply those two things together, what I'm actually multiplying is conjugates. So I've got my z times z bar, which is the modulus squared. So on the left-hand side, multiply those together. And on the right-hand side, multiply those together. Well, the left-hand side will become x squared plus y squared squared. And on the top of the right-hand side, 6 squared is 36, 2 squared is 4. The bottom, 3 squared is 9. And 1 squared, of course, is 1. And that works out quite nicely. That's just 4. So I now know that x squared plus y squared squared is 4. Well, x squared plus y squared must be 2. Notice I didn't put plus or minus 2, because I know it's going to be a positive number. If I'm adding 2 squares, it needs to be, well, when we're dealing with real numbers, it has to be a whole number. Okay, 6 squared, maybe I am being a bit generous.